In this video, we present our paper, SINE, Semantic-driven image-based NeRF editing with prior guided editing field. SINE is a novel 3D editing approach, which allows users to edit a photo-realistic NeRF with a single-view image or with text prompts, and then renders edited novel views with vivid details and multi-view consistency. Semantic-driven content generation and editing is a popular task in computer vision. In the 2D area, users can now generate or edit images with texts, strokes, or attributes with numerous fancy tools. However, similar editing abilities in the 3D area are still limited. For example, existing editing approaches might require laborious annotation, transfer global styles without strong semantic meaning, or only support category-level editing on faces or simple objects. In this work, we aim at realizing the capability of semantic-driven editing in two folds. First, we want the operation of 3D editing to be effortless, such as using editing from a single perspective. Second, we want the method to be applicable to real-world objects or scenes and preserve vivid appearances. To fulfill such demands, we propose SINE, which takes as input a pre-trained NeRF model and a single-view 2D editing with off-the-shelf tools, and outputs an edited NeRF model with consistent semantic meaning. The key technology behind this is a two-prior guided editing field, a geometry modification field and a texture modification field. The geometry field is used to deform the object, while the texture field is used to composite the original and modified textures. Specifically, the geometric modification field will deform the point from the edited space, in order to obtain density and color information from the template NeRF. The texture modification field outputs a color modification value ranging from -1 to 1. The color output of our editing field will be accumulated independently along the ray in our dual-volume rendering. This way, we obtain the deformed template and color modification image. Finally, we apply the color compositing layer, a U-net, to blend two rendered images into the final edited views. Editing a neural radiance field with just one image is highly ambiguous. To guide the optimization process, we need to introduce some neural priors. For geometry editing, we leverage neural implicit shape priors such as the deformed implicit field proposed by U-Dang or deep SDF proposed by Park. These neural decoded shapes can generate the implicit SDF field with an optimizable latent code condition. However, it is not straightforward to directly apply an SDF-based shape prior to our editing field. NeRF does not have an explicit surface definition that can be supervised by the shape prior. Thus, we begin by fitting the template NeRF geometry with a proxy mesh. We learn a forward modification field to warp the template proxy mesh to the edited space. The forward modification field is the inverse of the geometry modification field. It maps from the template space to the edited space and is supervised using a cycle loss. Then we use SDF loss and chamfer loss to ensure that deformed proxy mesh can be explainable by the shape prior. In our task, users only edit a single image, but we hope to propagate the editing effects naturally to multiple views with semantic meaning. Inspired by Splice proposed by Tumanyan, we use a pre-trained VIT model as the semantic texture prior and apply self-similarity constraint and CLS token constraint in a multi-view manner. Specifically, self-similarity constraint encourages the edited rendering and template rendering to share the same spatial structure. The CLS token constraint encourages the editing rendering to match the appearance of the target image. Furthermore, we learn a distilled feature field with DenoVit and filter the unedited semantic part using a feature clustering technique. The editing regularization facilitates precise editing of the desired region while preserving other content unchanged. Now, we will show editing examples of our method. We first perform geometric editing on real-world cars by enlarging or shrinking their tires and backs. As you can see, the edited cars can be rendered consistently on novel views. Here are other editing examples on the synthetic cars, where the car's body and tires can be effortlessly edited from a single perspective. Here are the geometric editing examples on the photo shape dataset, where the chairs are either bent or stretched locally, and our method can transfer such editing effect to the NeRF's geometry. Besides, we can also perform geometric editing on general objects, and even enable object deformable motion, such as the bird's flapping wings. Now we show examples of texture editing. We can add cookie tires and blue windows to the car on a single side view, and our method can faithfully transfer such editing into the 3D, where both sides of the cars are edited properly. We can even transfer objects' texture by giving target images downloaded from the internet, where the source and object's shapes can be different. As we have shown, the chair's bodies and legs are naturally retextured and matched to the target images. Moreover, when cooperating with text-driven editing such as Text-to-Live, we can edit NeRF with text prompts, and deliver vivid appearances with multi-view consistency. For example, we can turn a car into Swarovski blue crystal or ice sculpture, and change the pinecone with golden metals and dynamic burning effects. We can easily obtain a beautiful stained glass vase deck, or make it with a snowy appearance. And for the wooden table in the garden, we can precisely turn it into a shiny plastic round table, or a plasticine table made by kids, where the vivid view-dependent effects can be observed on the edited surface, while the background content is preserved unchanged. Finally, we show hybrid editing ability in several examples, where the geometry and texture can be jointly edited by users' 2D editing, which demonstrates the great editing flexibility of our method. Thanks for watching.